Swayam Prabha. Digital India. Educated India.
So, last time we were solving some problems which involved the angles mainly as seen by the surface, and then we were halfway through point problem 1.4, which deals with determine the sunset hour angle and day length for Srinagar and Port Blair for the following dates December 23rd, March 22nd and June 23rd. These dates were deliberately chosen. December and June, they have the maximum magnitude declination, negative in December and positive in June, whereas March 22nd will be the equinoctial day, does not matter whether it is 21st or 22nd. So, we will treat that declination to be 0. So, the first thing we calculated was the sunset hour angle, which is given by cosine inverse minus tan phi tan delta. So, I will specify December delta as minus 23.4 degrees and March as equinoctial day is 0 and June delta plus 23.4 degrees. So, we can latitude of Srinagar is 34.05 and then Port Blair so degrees and minutes. It does not make much difference whether you use it as a point or minutes converted to degrees. So, for Srinagar, first we shall do the calculations. December 23, omega s is cos inverse tan phi, which is 6757, and tan delta negative 0.4327, and this is cos inverse 0.2923, which is 73 degrees. So, your sunset hour angle is less than pi by 2, as can be expected in a winter month, and number of sunshine hours n s will be twice of omega s by 15 in degrees, which will be 9.73 hours. March 22nd, and since delta is 0, omega s is cos inverse of 0 should be equal to 90 degrees, and the number of sunshine hours n s will be 2 times 90 by 15 should be equal to 12 hours. You have an equal day and night on the equinoctial day. Then you go for June 23, you have got the sunset hour angle as cosine inverse same minus 0.6757 times 0.4327. Declination is positive. So, consequently, the entire thing is negative. This will be equal to 107 degrees. So, number of sunshine hours will be twice 107 by 15 degrees per hour, which will be 14.23 hours. You will notice that the previous number of hours which we got as 9.73 hours in December, and this as 14.23 in June, the summation will be 24 hours. So, for equal magnitude declination, a given location will have 90 plus some degrees as the sunset hour angle, or 90 minus the same number of degrees for the winter, or the corresponding negative or positive declinations. So, we will go to Port Blair. The whole idea is to show the effect of the days, which we have chosen the extremes of March, December and June, and then on the latitudes. Srinagar has the more or less the higher latitude in India compared to Port Blair, which has got a latitude of only what is the latitude? Okay, I think I must have given previously, and omega s, or you can see from the table that we have provided earlier. We will go for December omega s cos inverse minus 0.20 whatever is that tan latitude minus 0.4327, because it is December, you have a negative declination. This will be cosine inverse 0.8654, which is 85.03 degrees. And the number of sunshine hours Ns will be 2 into 85 by 15, which should be 11.33 hours. You will find that this is pretty close to 12 hours, and compare it to what we had for Srinagar, this is considerably higher. And if you go for March 22nd, omega s will be simply 90 degrees, since delta is equal to 0, and Ns will be 2 into 90 by 15, should be 12 hours. So, on equinoctial days, wherever you are, you have a equal day and equal night equal to 12 hours. And June 23, so omega s will be cos inverse of tan latitude of whatever times tan delta positive now, that should be equal to 94.96 degrees. Okay. So, you will find this is about 4.96 degrees higher, and the previous one is 4.96 degrees lower than 90. So, you have Ns the number of sunshine hours equal to twice 94.96 upon 15, which shall be 12.66 hours. Once again, the sum for the December and June will be 24 hours. So, this will be that much in excess of 12 hours, and in December it will be the same amount more or less, the corresponding declinations less than the 12 hours mark. So, if I make a summary so that we can draw some conclusions, day, I will set up myself a table, and I am giving the number of sunshine hours for Srinagar, and Port Blair. Okay. So, this is December 23, 9.73, 11.33, March 12 hours, and June 14.28 and 12.66. So, the following observations can be made if the latitude phi is higher. So, number of sunshine hours will be away from 12 hours. So, this is when I say it is away, it can be high, it can be low. So, for example, December it is lower and for June it is higher, right. And if consequently, if phi is lower, NS hours will be closer to 12 hours, whatever may be the season, and that is evidenced by 11.33, 12.66, that they differ only by 33 minutes and 66 in the summer and in the winter. Okay, whereas here you can see it is 9.73 hours and 14.28 hours. Okay. And of course, if the declination is 0, then there is no difference, or the effect of latitude is not felt, and you have equal day and equal night on equinoctial days, whatever may be the location. So, we shall go to the next problem, 1.5. When it is noon as per the clock time or Indian Standard Time, what is the solar time on January 20th in Mumbai, has certain latitude and longitude, and Kolkata and Kohima. So, these locations once again are picked up, so that one has the westmost more or less in India, and the other one the easternmost longitude in India. So, that will give the time difference compared to the standard time and the time so called solar time. So, we know that solar time is the standard time, that is the time that we see in the clock based on the longitude on which our Indian Standard Time is based, minus 4 times longitude of the standard time minus L location. So, this minus sign is for the east longitudes plus a correction, the so called equation of time. For LST India is 82.5 degrees. That is about 5.5 hours ahead of the Greenwich Mean Time. And the equation of time E is 9.87 sin 2b minus 7.53 cos b minus 1.5 sin b. You may please check with the earlier equations that we have written. I am deliberately repeating, so that at least one will be correct. B will be 360 times n minus 81 upon 365, where n is the day of the Julian date. Okay. So, we are having day as January 20th. So, n is equal to 20, and we are given that standard time as 12:00. It can be anything, the correction will remain the same. So, first we shall calculate B should be equal to 360 times 20 minus 81 by 365, right. N is 20 and that 81 is 81. This shall be equal to minus 60.16. So, E is 9.87, that is a constant, minus 0.8632 minus 7.53 times 0.4975. Those are the cosine angles of B and sine angle of 2B. 1.5 minus 0.8674, which is 10.96 minutes, because the equation of time is given in minutes. So, correction is in minutes, which is minus 10.96 minutes. Now, we will go to Kolkata, and solar time is 12.00 minus 4 times 82.5, the standard longitude, minus the longitude of Calcutta 88.27, minus the equation of time, which is minus number 10.96, and this comes to 12 hours 12 minutes. So, Kolkata time is ahead of the standard time, which can be expected because it is the eastern time, but you should also note that the equation of time E is not an insignificant number. Depending upon sign, if you look at that, that will go plus positive, it may aid or oppose the correction due to the longitude. Otherwise, if this had been plus or even 0, you would have had a higher time ahead of the standard time for Kolkata in the month of January. So, we go to Mumbai. So, solar time at 12 o'clock clock time will be minus 4, 82.5, minus 72.51. Please note that the longitude of Mumbai is less than the longitude of the standard time. This passes through Allahabad and this is to the west, consequently, it will be lower than 82.5. Minus, of course, the equation of time is independent of the latitude or longitude given by 10.96, which will become 12:00 minus 39.96 minus 10.96, which will come to 11 hours 10 minutes. So, you will find that there is a 50 minutes difference between the standard time and the solar time in Mumbai on January. Kohima, which is a eastern extreme sort of, solar time will be 12:00 minus 4 times 82.5 minus 94.07. The longitude is 94.07 E and east, this is 10.96. The equation of time which you have calculated remains the same. That should be equal to 1200 plus 46.28 minus 10.96, that is something like 12 hours 57 minutes. So, the solar time is much ahead of the clock time in Kohima, which is the eastern longitude, much more to the east of the longitude on which our Indian time is based. So, once again as a contrast, you can see Mumbai. Now, I have put it in the increasing order of the longitude, Kolkata, and then Kohima, 11 hours 10 minutes, 12 hours 12 minutes, and 12 hours 57 minutes. So, for a given clock time of 12 o'clock, if you look at the solar time in Kohima and Mumbai, there is a considerable difference, almost equal to 2 hours. Okay? So, this illustrates the point that the solar time can be different, quite different, up to an hour or an hour and a half, and depending upon the season, of course, because the correction E depends upon the day, and of course, the longitude difference, that is either it is a plus or a minus, depending upon whether you are to the east or to the west of the standard longitude on which the time of that location is based. So, India has one time zone only, and whereas US has got, of course, US across from east coast to west coast is much longer or much more farther than what we have from, let us say, Kohima to Mumbai, and consequently they divide into 4 time zones. So, in India I do not know, there was a move some time back to have 2 time zones, but nevertheless the difference appears to be significant. So, we will go to the next problem, 1.6. What are the sunset hour angles and the day length for the following? So, here I did not specify the names of the locations, but just these examples phi, for example, 15 degrees and lat declination 15 degrees, so on and so forth, up to latitude of 82 degrees and declination of minus 50. So, 5 examples were given. We would like to draw some conclusions out of computation that we do for the sunset hour angle and the day length for this following combination of latitudes and the declinations. So, first the formulae, omega s is given by cosine inverse minus tan phi tan delta, and the number of sunshine hours is twice omega s by 15 hours if omega s is in degrees. So, we will go one by one. First combination is latitude 15 degrees and the declination 15 degrees, not that phi is equal to delta. I just wanted to pick up a sort of average positive declination, which will be 0 to 23, 15 is a good number. Omega s is cosine inverse minus tan phi, which is 15, and tan delta, which is also 15. So, this will be equal to cosine inverse minus 0.71 0.78, which will be 94.11. This is a larger, this is 0. This is, let me rewrite cosine inverse 0.07178. I was just wondering because why this is so close to 90 if it is 0.71. So, 94.11 degrees. So, this is the sunset hour angle. So, you develop a field for the, since you know the functional dependence upon of cosine or sine whatever, and one should be able to have a check whether the number that you get is okay, is consistent with the number that you have over here. So, sunshine hours will be NS twice 94.11 by 15, that is equal to 12.5 hours. Okay. So, here I mean a decimal is a decimal. 12.5 hours means 12 hours 30 minutes. And second case is a higher latitude of 45 degrees and declination also high, which is more or less corresponds to June. Omega s will be cosine inverse of minus tan 45 tan 23 equal to cosine inverse minus 0.4244, which is 115.11. That is much more than the 90 degree of the so called average day. So, the number of sunshine hours NS will be twice 115.11 upon 15 should be 15.35 hours. So, compared to the common usual perception that the average sunshine is about 12 hours, if you have a high latitude and a high declination, you have as much as 15 hours plus something daytime. And the third, you have got phi equal to 45, delta is minus 23. So, we will take correspondingly a negative declination, which will correspond to June someday, sorry, December someday, and omega s will be, numbers will remain the same, except it will be positive 0.4244, which is 64.88 degrees only. So, this NS or the number of sunshine hours will be 2 into 64.88 by 15, which shall be 8.65 hours. Again, you will see that the previous summation of number of hour angles of 15.35 and 8.65, this will make a 24 hours, right, because declinations are equal, but opposite in sign at the same location. So, case 4 deals with an extreme latitude of phi 77 degrees and declination 15. I was cautioning, rather I have discussed in detail the cases where the latitude is more than 66.55 degrees. Depending upon the declination, you will have a little problem with the trigonometric relation of omega s is cos inverse minus tan phi tan delta. Let us see what the problem is. Omega s is cos inverse minus tan 77 tan 15, which is cos inverse minus 1.15, sorry 15, this point is not there. Let me rewrite cos inverse minus 1.15. You know that cos inverse is not defined when the modulus of the number is more than 1. So, this cannot be evaluated, but suppose this is an important statement or argument, and rather not a supposition, the fact. This cosine inverse minus 1.16 is reached after cosine inverse minus 1. So, what I shall do is I will take this as the limiting case and set omega s is equal to 180 degrees, because minus 0.1 for certain declination, for example, if you take let us say phi 77 and declination 13 degrees, you can trigonometrically also prove it. If this summation is equal to 90 degrees, that tan phi tan delta, the product will be just equal to 1, and the sign is according to declination being positive or negative. Okay. So, omega s is 180, then my n s will be twice 180 by 15, which is 24 hours. That means, if you have a latitude of 77 degrees and a declination of minus 13 or less mathematically, or magnitude wise minus 13, minus 14, minus 15, they are smaller numerically, but we consider them to be a higher magnitude. So, then I will be having a cosine inverse of a number of magnitude greater than 1. So, when declination is equal to minus 13, you have reached this 24 hours daytime, and beyond which it remains 24 hours, but it cannot be, since it cannot be more than 24 hours. So, this is one thing. Then where is the fallacy? Is this wrong, cosine inverse of minus tan phi tan delta? No, because we have put innocently theta is equal to pi by 2, and to find out my sunset hour angle or the sunrise hour angle. What we subconsciously thought was the sunrise and sunset is within 24 hours, which does not happen if the latitude plus the magnitude of the declination is more than 90 degrees, 90 degrees or more than. If phi plus mod delta is greater than 90 degrees, you have ns 24 hours or 0 hours. So, without solving, you just look at that phi plus delta, magnitude of delta, whether it is more than 90 or less than 90. So, to illustrate the point, the last one is phi 82 degrees. I made sure that it is definitely a large number, and minus 15 degrees. Omega s will be cosine inverse minus tan 82 and tan minus 15, which will be cosine inverse 1.906. Again I have the same problem. If the, even though it is positive, greater than 1 cosine inverse is not defined. So, I will presume that it has reached 1 and then gone on to become 1.906 in the negative declination. So, you will have omega s 0, since cos inverse 1 equal to 0 and 1.906 is greater than 1. What physically it means is the sunset does not occur just within 24 hours, but it goes to minus 15 to minus 23.45, then back to minus 15, and in this case, since I have a latitude of 82 degrees, only when it is minus 7 degrees, sorry, minus 8 delta or mod delta less than 8 degrees, we have a omega s, right, or else if all values of declination greater than magnitude delta 8 degrees or minus 8, minus 9, minus 23 back to minus 8, it will have 0 sunshine hours. Okay. So, N s is twice of 0 by 15 also is 0. Let me rewrite N s So, what we found is as the latitude increases, in the positive declination you have higher sunshine hours and low when the declination is negative, and the difference between the negative and positive declinations will decrease if the latitude is lower. In fact, if the latitude is phi 0 on the equator, there will be no difference in the sun daytime and the night time, whatever may be the declination or the month. And beyond, if phi plus mod delta is greater than or equal to 90, then you have got N s 0 or 24. Okay. So, you have all the time, that is exactly if you go to the North Pole for example, you have all the 6 months when the declination is positive, you have sun above the horizon, and all the days when the declination is negative, sun will not rise, it is below the horizon. So, this is so much about the angles of incidence and the time correction and the number of sunshine hours. Then we go to problem 1.7, estimate R b 1.7, that is the tilt factor for the direct radiation for a collector with 3 slopes 5 plus 15 and beta equal to 5, and then beta is equal to 5 minus 15 degrees from the horizontal, and south facing, that is gamma 0 for locations New Delhi, latitude is 28 degrees 34 minutes at 9:30 a.m. March 21st. Again, I thought I will pick up these dates to demonstrate the effect of extreme negative declination and extreme positive declination and 0 declination. Okay. So, this is south facing. I will write down the declinations first. Equal to 0, June, maximum positive 23.45, December is the negative extremum. Okay. My RB for a south facing surface is a simple formula I can remember. So, you should be able to remember cos phi minus beta cos delta cos omega plus sin phi minus beta sin delta over cos phi cos delta cos omega plus sin phi sin delta. So, for declination equal to 0 and phi equal to phi plus 15, sorry, beta equal to, or phi minus beta equal to minus 15. So, you will find that the slope is higher than the latitude. So, RB you can put down cos minus 15 times 1, because it is cos delta equal to cos 0 times cosine 930 will correspond to minus 37.5 time plus sin phi minus beta into sin delta, which is 0, upon you rewrite cos 28, that is cos phi cos delta is 1 and you have got cos omega okay, plus sin phi minus beta sin phi 28.56 times sin delta, which is 0. This will come to 0.766 by 0.6988 into 1.09. So, the RB factor is pretty close to unity. In other words, it is not much of an optimization. You have chosen the beta to be higher than the latitude, and on the equinoctial days it is not really an optimum, which will lead to a RB factor only slightly more than 1. So, you choose beta is equal to phi. So, we are first finishing for delta 0 and this is the second case, then RB will be cos phi minus beta, which is 0, cos delta, which is 0, times cos minus 37.5, that is cos omega, plus of course, the second term vanishes, which will be 0, by the same quantity 6968. This is, you can calculate 7.7933 by 0.6968, which is 1.138. Now, this is considerably more, if you look at it that way, than 1.09, which we got for phi minus beta is equal to minus 15. So, because declination is 0, this satisfies phi minus beta is equal to delta, because phi is equal to beta, right, which was one of the optimum orientations which we had considered in connection with concentrating collectives. Okay. Then you have got third case, beta is equal to phi minus 15 or phi minus beta is equal to plus 15. So, again delta is 0. So, R b you can write down cos phi minus beta, cos delta is 1 into cos omega is 0.7933 plus this will be 0 because of sin delta upon 0.6968. This is nothing but the cosine of the zenith angle theta z, which will not differ for a given time. This will be 0.766 by 0.6968 equal to 1.09. This does slightly better, right, because even though it is the equinoctial day, phi minus beta is positive and beta is less than the latitude and you have a higher factor. But at the same time, it is also the same thing that we found for phi minus beta equal to minus 15 in the first instance, because on the equinoctial day, if you have a surface like this, depending upon your beta, and this is the orthonormal to the surface, either you have angle of incidence like this or the ray coming like this, but these two angles will be the same. It will be on a conical surface around the orthonormal to the surface. So, you have exactly the same value as you have got for phi minus beta plus 15 and phi minus beta minus 15 for delta equal to 0. Now, we go to June and delta 23.45. So, first case is beta is phi plus 15 or phi minus beta equal to minus 15, and you can calculate your R b with all the numbers. It will turn out to be 0.6006 upon 0.828, which is 0.725. Now, you will find that this is even less than unity. That means, the direct radiation is not really augmented by this orientation in June. In June, the sun is pretty much high up, something like this. This is your slope and you have chosen beta to be higher than the latitude. So, it will be very near the away from the normal incidence, something like this, leading to a low R b factor of even less than 1. Okay. So, a horizontal surface would be better than this type of a wrong orientation. So, if you choose beta is equal to phi, your R b will be 0.7274 by 0.828 equal to 0.8785, which is of course higher than the previous value, but still less than 1. And the last is beta is phi minus 15 or phi minus beta equal to 15, and you have got a delta positive, right, which we have done it June 23rd. So, you will, for this condition, you will have 0.8046 by 0.828 equal to 0.9717. Okay. So, this will be 0.9717. So, you are still in the positive declination zone and you have chosen a beta higher than 5, right, and consequent lower than 5. So, that should be little favorable. Consequently, you have a value higher than the previous two occasions. And we go to December 23rd. Declination is minus 23.45 and with 5 minus beta equal to minus 15. So, R B will be cos 5 minus beta, which is 0.9659 times 917 cos delta cos omega, that remains the same 930 plus sin 5 minus beta 0.2588 into sin delta 0.3979. Please note that cos 5 minus beta is negative, so is sin delta. Consequently, this remains plus upon, I had to rewrite the whole thing, cos phi times cos delta cos omega plus sin phi into sin delta 3979. As I check, this is the same as this is the same as this. Of course, I could have committed mistake at both the places. This will turn out to be 1.79, pretty high value compared to less than 1 and 1.09 values. The next case will be beta is equal to phi, and you will have your R B. Please put down phi minus beta 0, giving you cos phi minus beta 1 and sin phi minus beta 0. So, that it is a simple way to calculate 0.7274 by 448 equal to 1.623, which is comparable to the previous one, though not higher. Then you have got phi minus beta is equal to 15, and you have R B as again 0.6006 upon 0.448 equal to 1.34. So, this is illustrates when you choose December, in general R B factors are larger, and so we will summarize to have a little moral out of this. A time is 9:30 a.m. and location New Delhi. Latitude 28 degrees 34 minutes north. So, day and corresponding to beta is equal to 5 plus 15, beta is equal to 5 and beta is equal to 5 minus 15. March, June, December, the corresponding maximum declination or 0 declination 1.09, 1.138, 1.09, and this is 0.725, 0.8785, 0.9717, 1.79, 1.623 and 1.34. So, this is beta greater than latitude. You have in December the highest. Beta lower than the latitude, you have the lowest among these three. The other things this summer will have lower RB factors in general, unless you orient your collector very correctly. And you have got March non-committal almost around 1, because declination is 0 when you change your beta from the latitude value by plus minus 15 degrees. Okay? That is it. We shall continue next time. Until then, bye.